welcome everyone to this week's Atto Fridays. We are pleased to have here as a speaker Professor Attila Czirják. He is a research fellow in the theoretical strong field and attosecond physics, theory and simulation groups at ALPS, and he's also an honorary associate professor in the Department of Theoretical Physics at the University of Szeged. He studied an MC in physics at the Attila Czirják University in Szeged before studying at the University of on a GAD Jahresstipendium, and this included a short but important visit to Wilhelm Becker's group at the MBI Berlin. So that's why you really notice how old you are, because I was a PhD student in the group when he was visiting. So yes, we are that old, but please don't tell anybody, although I'm saying this on the internet. So back in Hungary, at the University of Szeged, he completed a PhD in physics with a thesis on Wigner functions in quantum optics. And before joining ALPS, he worked for several years as a software engineer at Siemens, and then as a research fellow in theoretical physics at the University of Szeged. And he's a member of the public body of the Hungarian Academy of Sciences and the Holland Eötvös Physical Society, and has supervised numerous PhD, MSc, and BSc students. Now, he's going to talk about quantum details of atomic strong field ionization and high-order harmonic generation. And I would like to make the point that before quantum effects in attoscience became trendy, he was already doing that. So this was also one of the reasons why we are happy to have him here today, because now it's trendy, but when we met at the MBI, which was a long time ago, as I just said, we saw that he was already starting to do this, and his background is in fact quantum optics. So we're ready to start. Please feel free to start your talk. The floor is yours.
Thank you very much, Carla. I try to share my, yes, is it okay, the sharing? Yes, that's great. Okay, thank you much. Thank you very much, Carla. And so hello everybody. First of all, let me thank Carla for her kind invitation to this very prestigious seminar series. And the outline of my talk is like this. So I will cover a longer topic first, this quantum interference in strong field ionization. And then I will discuss three shorter topics. But before starting out, let me show the photos of my most important co-workers in the last 10 or 15 years. Most of these colleagues are affiliated both with ALPS and with University of Szeged. And I thank them again for their common work together. Okay, our first topic today is an interesting phenomenon that we published a few years ago. And I feel that that paper became too much condensed and not really easy to understand. So I will try to explain the most important points in this work in a more detail here. So first, I think for most of the audience, this picture, which I borrowed from the well-known paper of Ferenc Krauss and Misha Ivanov, is a very familiar picture that it tries to explain how strong field ionization and based on the three-step model, recombination and high harmonic emission in atoms works. This is a very successful model, but it still keeps room for improvement, especially from the point of view of quantum physics, and especially for the starting. I try to switch this pointer to I don't know. Yeah, yes, here to this pointer. So especially for this initiating step of tunnel ionization. This is another figure from the same paper, which then tries to emphasize how this strong field or this three-step model and the recombination in a multi-cycle laser pulse then leads to high harmonic emission, and in a lucky case to the emission of attosecond pulses. But this is the next figure is from a Nature paper of Adrian Cavalieri and co-authors, which is actually a typical pump and probe, attosecond pump and probe experiment, where the delay between the infrared pulse and the generated attosecond pulse can be set or can be scanned, and based on ionization measurements with this straking, so-called attosecond straking principle, time delays in photoelectron emission around 100 attosecond could be already measured in 2007. In all of these experiments, it is very crucial how much is actually the time delay between the generating near-infrared pulse and the generated attosecond pulse, because this fundamentally limits the temporal resolution of such pump and probe experiments. So, what are the other open questions in strong field ionization? Here in this talk, I will discuss only processes which either correspond to the tunneling or the over the barrier pathways of strong field ionization. And this figure, which I borrowed from a paper of Camus and co-authors, beautifully depicts the fundamental difference between tunnel and over the barrier ionization from the point of view of exit momentum. So for strict tunnel ionization, exit momentum in the longitudinal direction should be 0. But there are, for at least 10 years, experimental investigations going on to really measure the longitudinal momentum in strong field ionization. And one of the most interesting and promising results were published in this PRL of Camus and co-authors from the Heidelberg, Moshammer's Heidelberg group, where they first showed very convincing results, the experimental results, that the longitudinal exit momentum of the electron is probably not 0. Soon after, the Litvinov group from Australia used a different method, this attosecond angular straking, this also called Atto clock, with not linearly but elliptically or closely circularly polarized laser pulses, where they had the conclusion that for atomic hydrogen there is no temporal difference between the exit time and the peak of the pulse. So this so-called tunneling time for atomic hydrogen should be 0. But I stress again that this was for circularly polarized laser pulses. But most of the the high harmonic generation experiments, which are actually used in pump and probe, attosecond pump and probe experiments, use linear polarization, and clean linearly polarized case where the exit momentum was directly measured experimentally is not present to the best of my knowledge. At least this was the case a few years ago. And this is a summary of the situation with this exit momentum. This clearly contradicts conservation of energy if we consider only clean tunneling at a fixed energy, because the definition of the tunnel exit is that the total energy equals with the potential energy, from which follows that the kinetic energy is zero and the exit momentum should be zero. And this consideration contradicts to some of the previously shown experimental results. So we try to investigate this situation with theoretical and numerical simulation. And this roughly summarizes the basics and the framework of our work. We consider a few cycle laser pies with the usual sine squared envelope. We use very common parameters for large laser facilities like ELI ALPS. So titanium sapphires based near infrared laser pulses around 800 nanometer central wavelengths, and the peak electric field strength is set such that for in this simulation that for atomic hydrogen, this ensures that during the whole laser pulse tunnel ionization is possible. And the Keldysh parameter corresponds roughly to 1, but somewhat below 1. And we actually solved the 3D Schrödinger equation in length gauge. We use, of course, for hydrogen, this is obvious, but for many electron atom, we would use then single active electron approximation. And our method then switches to phase space methods in two steps. First, we go over from the three-dimensional solution to a one-dimensional reduced density matrix by integrating out the degrees of freedom which are perpendicular to the laser polarization. So we are then interested, we investigate only the quantum dynamics along the laser polarization direction. And we do this in phase space. So from this density matrix, we go over to this Wigner function, which is defined by this well-known formula. So yes, and in most of the results that I will show results which are around the peak of the laser pulse. And if we do the numerical simulation, then we have to be very careful. Therefore, we use our own code, which I just show you for this reference. I don't want to go in any numerical details here. And typical raw numerical results look like this, that this is how it would look in real space, how the electron waves leave the bound state in an atomic hydrogen. If I now create another snapshot close to the peak of the laser pulse, then we see that the electron wants to leave in this direction to the right, but it has already a large tail So because of its history, we are already closing to the peak of the pulse. So a few oscillations already happened. And we see that from this logarithmic color scheme that we have to compute a very weak effect with very high accuracy in order to be able to say accurate statements about this process. So now if we go over to phase space analysis and track the Wigner function's temporal evolution around the polarization axis, so the polarization direction of the laser field, which is the horizontal axis in this phase space, the phase space plot of the Wigner function, and the other axis is the electron's momentum. And this at the time zero is how the bound state of atomic hydrogen in this one-dimensional reduced Wigner function looks like. And in the next, I will show a short movie around the temporal evolution in this light red shaded temporal range. So closing and passing by the peak of the laser pulse. I should be able to press some here. Sorry,
Okay, all fine?
Yes, okay, now I try to show it, okay? I hope you can see it.
Perfect.
Okay, so, sorry. So this is how the Wigner function evolves in time. I repeat it. So we see that from the bound state, the temporal evolution of the Wigner functions is like a stream in the right direction and with increasing electron momentum values. And the color coding is the following. Red, or this orange shade, corresponds to the highest positive values of the Wigner function. As we go through yellow to white, we reach zero. And the different shades of blue, from lighter blue to darker blue, are more and more negative values for the Wigner functions. So we see a lot of non-classical oscillations here, and it is not really hard to recognize that this pretty much looks like some interference pattern. Okay, now the next slides we show two snapshots of these Wigner functions. So on the left we are close but before the peak value of the laser pulse, and on the right we are exactly at the peak value of the laser pulse. And in the bottom I show the cut of the potential of the atomic Coulomb potential, the combined atomic Coulomb and laser potentials combined with these plots. And I show with different line styles, different energy niveaus, for which now I show the classical trajectories, so classical particle trajectories in these stationary instantaneous potentials that are at the bottom for the different energy levels. And we see here there is this separatrix which corresponds to the energy which equals with the top of this barrier, and below this separatrix the trajectories are disjoint, so there are trajectories outside the tunnel and within, so on both sides of this tunnel. And for energy levels above the top of the barrier, we see, of course, continuous trajectories which lead the electron from the bound state into the escaping trajectory, so it can escape a classical electron. Okay, and now we see that these escaping classical trajectories actually quite well follow these outgoing streams of the Wigner function, and this all these considerations lead us that the instantaneous energy of this quantum energy instantaneous energy distribution is worth to study. So we numerically calculated the energy distribution and a different time instance. So we again are with time instance, we are closing the peak of the laser pulse, which corresponds to the red color, and we see that this is a logarithmic plot of this energy distribution, and we see that as we go closer and closer to the peak of the pulse, also energy levels actually higher than the tunneling, the initially considered tunneling energy, and also corresponding to over the barrier energies are populated. So this means that we have to consider a lot of we have to consider this process parallelly going on in a quite broad energy range, not only at the energy which corresponds to the initial state of the bond state of the atomic bond state of the electron. So this is an important observation, that this so-called this is also sometimes called shake-up of the atomic electron niveaus before the escape or the actual escape could happen. So this is extremely important. And in the next slides, I will show convincing curves of the probability current in different energy, corresponding to different energy regions with this color code, that there will be a current corresponding to the over the barrier process, a current corresponding to the narrow energy traditional tunneling process, and another color, this yellow or color, corresponding to the all of the tunneling processes considered simultaneously. And we show here this probability current along the z direction. This is again a logarithmic plot, and the color codes is the same as I just showed you. And with black we show the full probability current, and it is obvious that the traditional narrow tunneling current is almost negligible considered to the other two currents, to the all tunneling and the over the barrier probability current. And the sum of the all tunneling and over the barrier currents, probability currents, is not here is not equal to the full current, which means that there is a strong quantum interference between these different components. And this this means that so far we can infer that this escape process is smeared both in time and space. So it is not quite clear at all what should we mean by this picture that the electron leaves somehow, including tunneling. And where should it exit? Which point should we consider as exit point, and what time and with what momentum? All these ideas are actually connected with a classical particle desire that we should somehow imagine the best possible classical particle model for this complicated process. And for this, we need some kind of average momentum if we want to define some exit momentum for this process. And we are pretty convinced that this average momentum should be based on somehow on the Wigner function's phase space capabilities. And therefore, we need some kind of a quantum momentum. And it is actually quite pictorial to try to average the Wigner function momentum the momentum weighted by the Wigner function. That means we integrate the product of the momentum with the Wigner function along these first along the p axis and then along the z-axis. Then we of course get the expectation value of the momentum, and if we now skip the spatial integration, we just integrate this product with respect to the momentum variable, then we get some kind of something that depends on space and has something to do with momentum, but it is not actually the momentum, but what we get this way is actually the current multiplied by the mass. But we can easily find out that if we divide this quantity by the probability density, then what we get is actually this quantum momentum functions, which is sometimes called also flow momentum, and which can be calculated also as the gradient of the wave function's phase. So this is what we want to use. And if I plot this quantity, this quantum momentum function, I switch back to this pointer. So if we want to plot this quantum momentum function, then we get this black curve, which again, in those region of the phase space where the Wigner functions has any considerable non-zero value, quite well describes the escape process. And this is what I show with more plots. So we are again before, but close to the peak of the pulse, and we are now right at the peak of the laser pulse. And we see that this quantum momentum function beautifully follows this main positive stream of the Wigner functions, of the Wigner function. So then if we have this quantum momentum function, which seems to be a very useful and intuitive quantity, then which value of this function could be chosen as a suitable exit momentum? And this is a quite elaborate concept here, which is in most part due to my former PhD student Szabolcs Hak. and actually his idea was that we should choose a certain value of this quantum momentum function, and this value is chosen such a way that we consider now this quantum momentum function, which intersects these classical phase-based trajectories, but in such a way that for the reasonable parameter values, there is always a unique inflection point of this classical trajectory, that this unique inflection points is important because after these inflection points, this trajectory looks very so after this inflection points, the quantum trajectory, also the quantum process and the quantum momentum function also very accurately can be approximated with classical dynamics, because we are getting far from the Coulomb center, so the atomic center, and the laser electric field is dominant. And since we are in dipole approximation, quantum dynamics along a slope is actually the same as classical dynamics along the slope, and this is also, there is a deep connection in terms of Wigner functions for the time evolution in potentials which are at most quadratic in the coordinate. And so this is why if we choose this value of the exit point, then where the quantum momentum function intersects the classical trajectory, then this is a very reasonable exit momentum value, and the inflection point of the classical trajectory can be easily calculated, and it is actually in the same distance from the atomic nucleus, where other theoretical methods and also experimental results assume the exit region of the tunnel during tunnel ionization. So this exit position is also revealed in this way as an easily calculable coordinate. But all these possibilities start. All this process that we do this starts with specifying a temporal instance, a time instant, when do we consider this whole stuff. Okay, this time instance then defines the combined potential, and in this combined potential we look for energies, to which energies the corresponding classical trajectory has an inflection point which intersects the quantum momentum function. And this is how this whole definition has to be understood, that for any time instant we can define a tunnel exit position, and to this tunnel exit position at this time instant we can define a momentum value, which coincides actually with the corresponding quantum momentum value. So this is how classical considerations and quantum considerations can be matched in the best way, according to our opinion. And this is published in a quite condensed way in this paper. Now let's see how this works in real. Then, if we want to use this definition, here we are again in the phase space, but we plot here only quantum momentum functions at different time instants with black curves, and we then plot classical trajectories which start in this inner region according to this definition that I showed and tried to explain with this equation. And if we start this classical trajectory, so these are all possible electron trajectories, but of course, in a particular experimental process, only one of these could be realized, but these are all possibilities. And we see that these possibilities include such that actually depart to infinity, so they are directly ionized, and some others return to the ion core, rescatter, and afterwards are ionized, and other possibilities in between. And for all these cases, we see that these classical trajectories lead the escaping classical electron on the trajectory in such a way that at later time instants they are still in very good agreement on the same phase space position as the quantum momentum function at the specified later time predicts. So these initial conditions that we discussed in detail are in this way very good initial conditions because they reflect the later quantum evolution also. And this property of the connection of the classical with the quantum evolution can be also shown by considering only that part of the escaping quantum wave function which actually can reach a detector. This is called positive energy, positive momentum wave packet. I don't go into the details how we compute it, but after computing that part of the wave function which can reach a detector at infinity, in the right direction, we can propagate it backwards with quantum solver, and we can see what did this wave packet look like earlier. And if we now go back just before the time instant, before the main peak of the laser pulse arrives to the atom, then this quantum back-propagated wave packet looks like this. And at a bit later time, it looks like this. And if we now put classical trajectories onto the different points of phase space on this Wigner function, and we let them evolve according to classical dynamics, then we see that at a later time, these hypothetical classical particles, so this possible escaping electron pathways, still very well match the Wigner function of this escaping wave packet at the specified time. So this, for us, is quite convincing that we are on the good track to actually resolve this problem of non-zero exit momentum, and we hope that our proposed value based on this quantum momentum function could be verified experimentally sooner or later. So I just tried to summarize with this slide for this first main part of my talk, and I anxiously check the watch. The last point here I did not explain. You can read it in this paper. Szabolcs invented a reconstruction method from measured data we could actually somehow recover really this non-zero exit momentum. So let me see. I have roughly 10 minutes left. So I skip this model potentials part, sorry, and I briefly discuss quantum entanglement, this is the most this is the shortest from the other three. And quantum entanglement in strong field ionization is a new kind of viewing this ion and electron that are created by this strong laser pulse during strong field ionization. If the electron does not recombine, but finally it escapes to the infinity, so the ion really gets, so the atom really gets ionized, then it is quite, we were among the first to consider what is then the connection, the correlation between them, and the deepest correlation between ion and electron is given by the quantum entanglement of these two particles. And here we actually have, of course, the usual Hamiltonian, and the main point is that in the relative and center of mass coordinates, the quantum state is we consider it always as a product state, but it will be not a product state when we consider the state in the electron and in the ion core coordinates. The ion core coordinates are labeled with C for core. So the two particle wave quantum state, or the wave function, is a product in the relative and center of mass coordinates, but it is not a product in the electron and ion core coordinates. And there is a standard method how to compute the quantum entanglement for such two particle systems. We have to actually make this Schmidt decomposition of the two particle wave function. And if this is a real sum, so more than two terms, more than one term, so at least two terms, then we say that this quantum state is entangled. And we can do this Schmidt decomposition based on the reduced density matrix of the two particle quantum state, which is defined like this. These reduced density operators, both for electron and ion core, have the same eigenvalues. So we have this P eigenvalues, P for probability, and the corresponding eigenvectors we also have if we make this reduced density operators. But actually, for quantifying the quantum entanglement, we only need actually these P eigenvalues, because from these P eigenvalues we can compute the Neumann entropy, which is defined with this familiar formula. And this Neumann entropy is one of the most important measures for quantum entanglement. And we, based on numerical simulations, we computed this Neumann entropy and also the linear entropy for the process of strong field ionization of hydrogen with this familiar sine-squared envelope laser pulse. And we observed this very interesting feature that at the zeros of this laser pulse, both entropies, both the Neumann and the linear entropy, have local maxima in a reasonable range of peak electric field strengths. And this was done already earlier, but in a few years ago, we wanted to check if this is also true. Sorry, I didn't mention this was a one-dimensional model with a one-dimensional model potential, so with this artificial one-dimensional atom. But later we repeated this and we checked if this is also the case for a real three-dimensional hydrogen atom. And there is a slight complication because this is a numerically demanding task. So we, with Szilárd Majorosi, we introduced a simplifying assumption which made the numerical computation actually possible to be carried out. And for this mutual entropy along the laser polarization direction, which is the closest measure to the Neumann entropy for the one-dimensional case, we had pretty much the similar result that after oscillations, the entropy always has a local maximum at the zeros of the laser pulse, and depending on the field strength, the electron and ion core particle pair has considerably higher entropy than before the arrival of the pulse. But if we add up also the two other spatial directions, then a surprising result came that adding up all three Cartesian components of mutual entropies, there is a slight decrease, not an increase, in the full entropy of the system. So this was a big surprise for us, and it is still an interesting question, and it would be very good if measurements could be carried out to check whether this simplification has a strong effect on the results, or are they really close to reality. So also in the last few years, also other research groups joined the research on entanglement. Here I show one of the most interesting proposals from Levenstein's group, where they consider non-sequential double ionization of different atoms, not only helium, but also other atoms, and they looked for electron-electron entanglement, not electron-ion entanglement. So this leads to the concluding of this second short topic. And here I just mentioned that besides electron-electron or electron-ion core entanglement, of course, any particle with photon or photon-photon entanglement between different high harmonic modes is also present and interesting and has high scientific potential to explore. So I assume, Carla, I should finish, and now I just keep the last part, which was about quantum optics of high harmonic modes, and I come to my last slides, where I would like to encourage you to look for contact with us if you are PhD students or postdocs, or just want to be users of any ELI facility. We are glad to work with you in any form of cooperation. With this, I would like to thank you for your attention, and I'm ready to answer your questions if I can. Thank you for your attention.
So thank you so much for your talk. It was really interesting to see these quantum aspects here being discussed more and more. Now, are there questions or comments from the public? Either type it in the Q&A tab or raise your hands, and we can let you in to talk. I mean, one question that I would have is, because I saw you were computing those eigenvectors and eigenvalues, and for me at least, in terms of doing that in practice, I was wondering how you were doing this, because you have, in principle, you don't have an eigenvalue problem, at least not that I can see, because you have a time-dependent problem and you have a continuous basis, right?
Yes, but we do it for each time instant that we are. So we track it time step by time step. So we repeat at every time a step this, and in 1D this I could do it myself, but for 3D that's a horrible task. So I looked for Szilad's help. He was my PhD student, and he was very professional in numerics and programming, and he spent much time on this project.
Okay, yeah, I mean, because so you compute the eigenvalues, you track the wave function as a function of time,
yeah,
and then
I go back
every time.
I go back,
okay.
And so we take the wave function at each time, okay, and we compute the density matrix at each time, okay, and this is in a spatially discretized way. So this is a matrix, okay, it's a huge matrix, and we just with brute force do its eigenvalue problem, okay, and then we have then we have these eigenvalues, and for the specified time, and from these eigenvalues we compute simply the Neumann entropy. So it's nothing magic, but brute force numerics.
Yeah, okay, but good to know. But the other step is not that brute force when you change the basis to make it separable. That one is actually very clever, because you get rid of a lot.
Yeah, okay, but in these coordinates, so in electron and ion core coordinates, the quantum state is not separable.
Yes, I agree.
Okay.
One question also, because you mentioned about this tunnel exit and tunneling, and this has been a big controversy in our field. So what would you say is the solution for this controversy? Is there a solution? Because some people say tunneling happens instantaneously. Some people say there is a tunneling time. Some people say this is fuzzy. So I understand that we are on YouTube. You may want to keep yourself out of controversy.
Okay,
but what would be your...
I go back. So all I did here, maybe I come back to this definition. So this T here, this T is not tunneling time, okay? This is tunnel exit. This can be considered as tunnel exit time, okay? But we don't know when, what should we consider as tunnel input time, or where the tunneling starts. So we don't claim that we know what is the tunneling time, in that sense that you mentioned, that how much time should tunneling take, if any. So this is just a tunnel exit time, which is connected to tunnel exit position. And from these two, we can then logically define a tunnel exit momentum. So all these three quantities, tunnel exit time, tunnel exit momentum, and tunnel exit position, are connected. Okay, and all these and this tunnel exit time is not unique. According to our understanding, there is a finite probability of this escape to happen in the classical point of view in a reasonable time range, and therefore in a reasonable exit position and exit momentum range. Okay. Okay, so it is smeared both spatially and temporally, and this is in accordance with this observation that this whole process, goes through this important broad energy range simultaneously. Okay.
Okay. Very nice. Thank you. There's a question by Wilhelm Becker. Thank you for a nice talk. Is there any way to experimentally observe the consequences of entanglement in view of the large MCME ratio? This is when you consider the...
I see. That's a very clever question. Thank you very much, Wilhelm. I don't have any proven idea for that. I have already ideas that should be discussed with experimental experts. But if you are interested, I would be very happy if you could be involved in this question. I will contact you.
Actually, William, you can unmute yourself. You are promoted to panelist, so in a webinar setting you can speak. So if you'd like to continue the discussion now or say hello, feel free to do so.
Hello.
Can hello, you hear me? Nice to see you. Hear you.
Yeah. Let's see. Can you see me? I don't know. Doesn't matter.
Not yet, but we can hear you.
Yeah.
We can
well, okay. It's probably not the place to discuss this in detail, but maybe we can follow up later on this.
Yes.
Okay. Thanks very much.
I thank you very much.
So are there any further questions, comments? People are quiet today. No. What is happening to people? Come on, say hello.
I try to do my best, but maybe I was not clear enough.
Don't worry, it's Friday afternoon. People are tired.
Okay.
So it has nothing to do with you being clear or not. I think it's a great idea. And I think also people have been doing classical stuff for too long and sometimes taking it very seriously. So I think it's great when we start to look at entanglement and all these things that are happening.
So at least as some summary, maybe I should tell that in our view, actually, the quantum physics of this whole strong field stuff and harmonic generation, strong field ionization is extremely interesting, very connected to fundamental problems of physics, and we always feel that no matter how far we get, we are still only at the beginning. So there is pretty much to do yet, both theoretically and experimentally. So I think I think Carla, you also participated at this workshop in Bad Honnef roughly 10 years ago. Do you remember Bad Honnef?
Yes, I remember. Yes.
Okay. There, Misha Ivanov said that roughly in each 10 years, we have the feeling that we understand atomic strong field ionization, and this repeats roughly in every 10 years. Now we understand it. Oh, now we understand it. This seems to be very, very true for me.
Yeah, very good. But if we understood everything, we would be out of jobs.
Yeah.
You know?
Okay.
So, Anonymous attendee, hello, Anonymous, nice to meet you. Very insightful talk. I really liked how the phase space analysis work led to a method to define the tunnel exit momentum of the electron. Thank you very much.
Ooh, sorry, Carla, could you repeat the
Yes, I mean, you
essence?
can see also if you click the Q&A tab, you can see that someone who is anonymous liked very much how you analyzed the phase space and
I see. Okay,
the
so
method.
there is no question actually. Okay,
No,
thank you.
the comment.
Okay, okay, thank you very much for this comment. Okay.
Yes, because this is like a big issue in our field.
Yes, I agree. This is why it was really interesting for me. Okay.
We organized once a panel discussion on tunneling, which was a real battle when the people are talking about making a rematch because no conclusion was reached.
Okay.
So it's like we do this
Yes.
conference every 3 years about controversial topics. So,
yes, I know. Okay.
yeah,
I read one of your papers about it. Was a summary paper about it. One of these. Yes, okay. I like this concept that you try to really revive this aspect of science, doing science, that debating different concepts.
Yeah, people should fight more, but in a nice way. You know what I mean?
Yes, I agree. Okay.
Yes. Okay, so are there further questions, comments? I know it's Friday afternoon, but it is a good chance to talk to our speaker. If you don't want to be all over YouTube, we're going to close now our talk, and you are going to have time to talk to him afterwards, so hang in there. And if not, whoever is watching on YouTube, we had some people today. Take good care of yourselves and stay safe. And we wish you a great weekend and see you in 2 weeks.